Well, guys, I said I was going to give you a video about taking a capacitor network and simplifying it down into one single equivalent capacitor. And that's what we're looking at right now. This is example 10 from your packet. So you should probably have it out in front of you. The other thing that would be good for you to have in front of you, and I'll put it on the screen, is the two equations for combining your series capacitors and parallel capacitors, meaning for finding equivalent capacitance. So remember, for series it was 1 over C equivalent equals 1 over C1 plus 1 over C2 plus however many more you have, right? Okay, and then for parallel, that was really straightforward. It was just the sum. The equivalent capacitance for two or more capacitors wired in parallel is just going to be the sum of their individual capacitances. All right, so if I'm looking at this capacitor network here, I'm wondering how ought I to begin to simplify it down, because there's a lot going on, right? There's a junction or a branch, right? Branch there, right? So you have three different parallel branches, and it's too much to process all at once. So what you do is you start with digestible chunks, right? What is a bit here that I can definitely say, all right, that's a simple thing, I can combine those very easily. Where I'm going to start is with those two right there. Those two are definitely in parallel with each other. Okay, so if I were wiring this up myself, if I wanted to do it more simply without, say, getting a 1 microfarad and a 2 microfarad capacitor and wiring them in parallel with each other, I could simply replace them with a 1 plus 2 is 3 microfarad capacitor. All right, so in other words, this circuit that is drawn here is equivalent to this. Now, the next step as I'm going through this is, I mean, there's still a lot of capacitors here, right? I don't have a single equivalent capacitor yet, so I'm not done. But I can look at that 1 and that 3 there and say those are in series with each other. And for that matter, the 1 and the 2 here are in series with each other as well. Which means that I should be able to add together the 1 and the 3 by saying, all right, use my equation down here for series. 1 over 1 plus 1 over 3, because 1 and 3 are my two capacitances, is going to equal 4/3. Rookie mistake. That means the combined capacitance is 4/3. It is not. Because everything here is 1 over, right? So 4/3 is 1 over the equivalent capacitance, which means that, in fact, my equivalent capacitance for those two is 3/4 microfarads. I'll do a similar thing with the 1 and the 2, right? We have 1 over 1 plus 1 over 2 is 3/2. Flip it over 2/3. So the next stage in simplifying is going to give me this. There it is. Okay, so just like I said, 3/4, 2/3, and 1. At this point, I could go one step further, right? You could look at the 3/4, the 2/3, and the 1 microfarad capacitor and say to yourself, oh, those are all wired. Right now you should be thinking, how are they all wired? Series or parallel? They are all wired in parallel, which means that the equivalent capacitance for this network now would just be the sum of those three. So if I take 3/4 plus 2/3 plus 1, there's some algebra, or not, adding fractions involved. Okay, but not that bad. We should be able to add fractions. And you'll end up with 29/12. Okay, and that would look like this. 29/12 microfarads. I may produce another video later on where I show you how to find the charge and potential across each of the different capacitors in that network, because that is the second part of that question, but we will hold that off for later for a second video. All right, I hope that helped. I hope that made everything make sense. If you have questions, please email me. Thanks very much.